Hook/opening. Imagine you're walking through a revolving door in a high-security building. Normally, the door is secure, it keeps unwanted guests out. But imagine if someone figures out that tapping the glass in just the right way makes the door open for anyone, no questions asked. Suddenly, that highly secure entrance has a sneaky weakness. This is not too different from what happens to machine learning models when they're attacked with what we call adversarial examples, tiny tweaks that trick even the smartest AI into making bad decisions. Today, we're going to explore an advanced but crucial area of AI safety called adversarial robustness via certified defenses and stochastic differential equation-based neural networks. I know, it's a mouthful. But let's break it down together in a way that everyone here can grasp. Topic introduction. First, what's the central issue? Machine learning models, especially deep neural networks that power everything from your phone's face unlock to self-driving cars, can be shockingly gullible. By ever so slightly changing the pixels in an image so subtly that your eyes wouldn't notice, an attacker can make a neural network misclassify a stop sign as a speed limit sign, or a dog as a cat. This is dangerous where stakes are high, like in autonomous vehicles or medical diagnostics. To protect against these attacks, researchers develop techniques known as adversarial defenses. But most defenses can eventually be fooled, given clever enough attacks. That's where certified defenses come in. They are methods where we can mathematically guarantee, within some margin, that the network's decisions won't change under certain attacks. Think of a door that is not just strong, but whose strength we can prove with math. Now, a cutting-edge approach to building these certified defenses uses tools from the world of stochastic differential equations, or SDEs, brought into the heart of how neural networks process information. Core concept explained. Let's untangle this concept gently. Stochastic differential equations are mathematical recipes for describing systems that evolve over time but with an element of randomness, like predicting the winding path of a dust particle floating in a sunbeam. If regular neural networks process data in a somewhat rigid, fixed way, SDE-based neural networks inject controlled randomness into their computations, sort of like adding wiggle room to each decision the network makes. Why would we want to do that? Here's where the magic of robustness comes in. By purposefully introducing uncertainty into the network's decision process, it becomes much harder for an attacker to predict how the network will react to their clever tweaks. It's as if our revolving door now spins unpredictably, slipping through is much harder if you can't anticipate its motion. But that's not all. Certified defenses leverage this randomness mathematically. Researchers can use properties of SDEs to estimate and even prove the likelihood that the network's output won't change, even if the input is nudged in tricky ways. For example, imagine shaking a picture slightly in many random yet controlled directions and seeing if the network's answer remains the same. If so, we can certify with high confidence, no attack within this shaking range will change the result. Scenarios and use cases. So, where does this matter in real life? Let's look at a few scenarios. First, autonomous vehicles rely on visual identification of street signs. In the wild, attackers could place stickers or subtle marks on a stop sign to fool an AI camera into seeing it as something else, possibly causing accidents. SDE-based neural networks with certified defenses can provide guarantees. Unless the tampering goes beyond what's practically possible, the model's decision won't change. Second, consider medical image analysis. An adversary with access to the AI system could subtly alter a scan so that a benign tumor is classified as malignant, or vice versa. Certified robust models help medical professionals trust that the diagnosis is not only accurate but also resilient to manipulation, something standard neural networks can't always promise. A third scenario lies in content filtering. Think of AI moderating social media posts. Adversaries might try to modify hate symbols or objectionable content in subtle ways to sneak past filters. With certified defenses, platforms can assure users and regulators that the system isn't easily tricked. Importance and benefits. Why should we care, aside from the technical fascination? As AI systems become more embedded into critical decisions in society, from cars to courts to commerce, the integrity and security of those decisions matter more than ever. Adversarial attacks aren't just theoretical, there are demonstrations of bypassing facial recognition or manipulating financial trading bots. Certified defenses, especially those built on SDE-based neural networks, represent a leap forward. They don't just play catch-up with attackers, instead, they set provable boundaries, giving developers and users trustworthy assurances. This could pave the way for regulatory approval in high-stakes fields and even provide peace of mind as AI's reach expands, knowing that these tools are not easily duped. Potential questions in listeners' mind. At this point, you might be asking, does this mean human engineers are out of the loop? Can networks now defend themselves completely? Not quite. Human expertise is still crucial in designing, tuning, and validating these models. Certified defenses set strong rules, but creative attackers might find new, unforeseen angles, so ongoing research and vigilance remain critical. Another common question: is this what's used in big AI models like ChatGPT? Not directly. While robust and certified defenses are a hot area of research, most massive language models like ChatGPT don't yet employ SDE-based certified robustness for the text they generate. However, related ideas are influencing how we think about securing all types of AI systems, and over time, these methods could become standard as industry priorities evolve. Closing. To sum up, adversarial robustness via certified defenses and stochastic differential equation-based neural networks isn't just a long, complicated phrase, it's a glimpse into the future of trustworthy AI. By blending randomness and mathematical guarantees, it gives us the tools to build neural networks that stand strong against the subtlest subversions. As AI continues to wield greater power, approaches like these will be foundational for ensuring